Sometimes CompTIA drives me a little bit insane. They took out one aspect of symmetric encryption that I personally find extremely important. This is no longer on the objectives of the exam. However, I think as a technician, you need to understand the different types of block modes used for symmetric encryption. So watch this episode from the previous version of Security Plus. It's good stuff and it's going to make you a better tech. Symmetric block mode encryption is the cornerstone of pretty much everything we do in terms of encryption on the internet. And it works really well and it's very, very robust. But block encryption has a problem. Now, what I'm going to use is AES encryption as an example here. But what we're going to do is set up a little diagram, and I want to show you one little problem with block encryption. So let's start off by setting up a little encryption machine. So I want to start off our diagram here. In the upper right hand corner, let's make like a little conveyor belt of ones and zeros that are coming out to be encrypted. Remember, the whole idea of block mode is that it's going to take a chunk of ones and zeros and it's going to drop it into this encryption block where we apply the key, and then it is output as encrypted text, and I'm going to make another little conveyor belt here as we show each block. Now I want you to look very closely here. So as this runs, you're going to see that we're only grabbing 8 ones and zeros at a time. Now if you've been watching in other episodes, you know that we don't do anything in little 8-bit chunks. Today's powerful symmetric block encryptions like AES are going to be working at an absolute minimum at 64-bit chunks. The reason I'm doing little 8-bit chunks is just to make the diagram a little bit easier for you to understand. So the bottom line is that with any form of symmetric block mode, if you grab a chunk and you drop it through your encryptor with the key and you output it, every time you grab a 64-bit chunk or whatever the chunk size is, and you keep encrypting it with the same key, you're always going to get the same output. So this mode, which we call electronic code book, is a bit of a problem in that we run into situations where patterns can appear. Let me give you a great example. This cute kid right here is my little grandniece Maddie. Now, what I want to do is take this image and I want to encrypt it. So the problem we run into is that the individual pixels of most images are going to be of a particular size. And it depends on the type of file format, JPEG or whatever you might have. But what will start happening is if we encrypt this in ECB mode, it's going to end up looking something like this. Yeah, all the individual pixels are encrypted, but because they're encrypted with the same block size, with the same key, they keep coming out absolutely identical. So it may not be a black pixel, it might be a yellow pixel, but the bottom line is I can still make out Miss Maddie there. So we've got a problem with symmetric block encryption. The problem is that we can generate patterns that can actually give away our data. Now in that example I just showed you, we're using a photograph. It's pretty easy to make that out. But we can run into the same types of problems with voice, with databases, with all kinds of stuff. The patterns aren't as easy to show on a video, but the same problems exist. So what we do is we don't use ECB mode with our symmetric encryptions. What we do instead is we use different types of what are known as block modes to obfuscate the data better. So there are a number of block modes that are on the exam. So what I want to do is go through each one of them. The basic trick to all of these different block modes is that we're going to encrypt something and then we're going to use that encryption to help encrypt the next one. So we end up, they're really kind of like a chain. And they're actually very interesting. They're all on the exam. So let's go through each and every one of these because you're going to see it. You ready? The first block mode I want to show you is called cipher block chaining, or CBC. So we've got our encryption methodology here. We've got our plain text at the top. We've got our output text, which is going to be, we'll start loaded there at the bottom. And here's our encryption. But we're going to do something different this time. First of all, we're going to add something called an initialization vector. So here's an initialization vector. It is the same size as the blocks themselves. And what we're going to do is before we encrypt it, we're going to take that first block and we're going to do an XOR against this initialization vector. Then we're going to go ahead and encrypt it. and put the encryption output down there. But we're also going to keep another copy, and this is going to be used for the next block. And that way, what's happening is that we're not going to get the exact same data for every different key because we're actually changing it a little bit every time. Next is cipher feedback. Now, with cipher feedback, or CFB, you're going to see it's actually pretty similar to what we just looked at. In this case, though, we're going to take that initialization vector and we're going to go ahead and encrypt it. We encrypt the initialization vector, and then we take the output of that encryption and we XOR it to the first block. So here we go ahead, here it outputs, and it just gets XOR'd to that first block. So it comes in, we put one copy of the output down onto the ciphertext, and then we go ahead and cycle that output and use that, and we go ahead and encrypt that for the next one. Third is output feedback. Now, with output feedback, what we're going to do is we're going to take one initialization vector and we're going to go ahead and encrypt that. We're going to take the output of that encryption and we're going to XOR it to that first block. Then we go ahead and put that output there. Now, in this case, what's actually kind of interesting is we just keep using that same initialization vector. CTR, or counter, is a little bit different than the others. In this particular case, what we're going to have is a nonce value. Now, in this particular example, it's only 4 bits long, but again, in the real McCoys, it's much bigger than this. And then a counter value that continues to increment in binary. So in this case, what we're going to do is we're going to combine the nonce and the counter. We go ahead and encrypt that, and then we take the first block of the plaintext and XOR it to create the first block of ciphertext. The next time we do this, all we do is we increment the counter. So the counter gets incremented, we go ahead and concatenate that to the nonce, we encrypt all that, and then we go ahead and take that and output that to the second block. The power of these different forms of block modes is that they get around this limitation of symmetric block encryptions. So by using anything other than ECB, we should be able to do something like this. So here's my cute little niece Maddie one more time, and applying a good block mode to it, it should look something like this. Totally randomized data. For the exam, make sure you're aware of the fact that, number one, nobody uses ECB anymore. It's simply not done. There are a number of different block modes out there, and different types of crypto systems will take advantage of them depending on what they need for their particular application.